Hello, welcome to the second lecture on approximation algorithms. In this lecture, I will introduce some more examples of approximation algorithms. Moreover, I will introduce two important concepts. One is called inapproximability and the other one is the use of linear programming to arrive at good approximation algorithms. Anyway, let us continue our study. Okay, let us look at a second example of a problem which has good approximation algorithms. This is called the minimum set cover problem. This is basically an extension or generalization of the vertex cover problem, of which we have seen a couple of approximation algorithms. One is logarithmic time, I would say logarithmic approximation ratio. The other one is a constant approximation ratio of 2. So this is a very similar problem. Let me introduce this first. So let X be a universal set x1, x2, x3 consisting of m elements x1, x2, x3 up to xm. Of course, we always assume that this is a finite set with m elements. And suppose that a collection of subsets of x is given. Okay. It's also a finite collection of subsets s1, s2, s3 up to sn. Each one is a subset of the universal set X, and it is also given that the union of these sets is the entire set X. Okay. Now the question is, can I throw some of these subsets from this collection and still have this union equal to X? Okay. So formally, let us take some indices I1, I2, Ik. Some of these indices 1, 2, 3 up to n, and the subsets corresponding to these indices are Si1, Si2 up to Sik. So these sets are said to cover X or are a cover of X. These sets constitute a cover of X if their union still remains the entire universal set X, so equal to 1 to K. Okay. And the minimum set cover problem has to deal with finding a cover with as few subsets as possible. Okay, so to find a cover such that this K, the number of subsets in the subcollection, is as small as possible. Okay. Actually, you see that the vertex cover problem is a special case of the minimum set cover problem. Why? So, in a vertex cover, X is the set of edges and the subsets are the vertex, basically vertices. So they correspond to Si is the set of all edges E such that I is an endpoint of E. And your task is to find, so this is for I in V. So your task is to find a smallest collection of vertices such that all edges are covered. Okay, so this is basically a special case of generalized set cover problem. And the algorithm that I am going to discuss about this minimum set cover is directly derived from the greedy greedy vertex cover algorithm. So this is this. Let us consider this. So this will be the set cover initialized to empty. As long as there are more elements to cover, that is x has not reduced to the empty set, find a subset with the maximum current size and add S to this collection U, and since all the points in S are covered, we simply remove all the elements of S that are not yet removed from X, and for all the remaining subsets Si, including S itself, you just remove the common elements from Si, and if Si is empty, remove Si from the collection. Keep on doing this until all elements of the universal set are covered, and when you are done, simply return this collection of subsets, return U. Okay, so this is exactly the same as the special case of vertex cover. So this is exactly the same algorithm as the greedy algorithm for minimum vertex cover, and the analysis is also exactly the same. So I leave it to you. I only mention that analysis is exactly the same, and we arrive at an approximation ratio of theta log, and that is also tight, because the vertex cover tightness example is also an example of tightness for set cover, minimum set cover. Okay, now let us see a new problem of a little bit different flavor. This is called the traveling salesperson problem. So you are given a complete undirected graph G equal to V comma E. Okay. Complete means for all possible choices of two vertices, there is an edge in this. Moreover, there is a cost function C that associates a positive real cost to every edge. Okay, every pair of this. And we assume that this cost is symmetric because we are talking about undirected graphs. So we assume that C is symmetric. That is C U of U to V equal to C V to U for all U V. In V, of course, I assume U is not equal to V. Now, the vertices in this graph may be considered as some locations like cities, and edges are highways or airways between pairs of cities, and this cost is basically the cost of travel from one city to another, and we assume that the cost, the to and fro costs are basically the same. U to V cost is same as the V to U cost. Okay. So now suppose that a traveling salesperson starts from one city, goes to another city, goes to another city, goes to another city, makes a complete tour of all the cities, but he visits each city once and only once, and eventually he comes back to the city from which the tour started. So this is basically a Hamiltonian cycle. Okay. Each vertex is visited once and only once. Since this is a complete graph, there are many Hamiltonian cycles. Something like n minus 1 factorial by 2. Okay. And the total cost of travel on this Hamiltonian cycle is the total cost paid by the traveling salesperson. And the problem is to find the Hamiltonian cycle which minimizes this total cost. Okay, so to find a Hamiltonian cycle Z in G for which the sum C of Z of all H costs on Z is as small as possible. So this is once again a minimization problem. Okay. So why is TSP in NP? Let us have a quick look. Given a sequence of vertices, it is easy to check whether it is a Hamiltonian cycle or not. Moreover, given any Hamiltonian cycle, it is fairly straightforward to compute the total cost of all the edges. Okay. So it is easy to compute the total cost of a Hamiltonian cycle. Okay. So this is a problem in NP for optimization problems. Now we will also study a special case of this traveling salesperson problem, which is called Euclidean TSP. In fact, we will start with an approximation algorithm for this Euclidean version. Here, we assume that the vertices are cities in the two-dimensional plane. Actually, we do not require two-dimensional plane. We may have three-dimensional, four-dimensional, any arbitrary dimension. Anyway, for simplicity, let us assume that we are talking about cities on a two-dimensional plane. And these cost functions are nothing but Euclidean distance between pairs of cities. So CUV is nothing but the Euclidean distance, which is definitely symmetric about its two arguments. Now I will tell you a two approximation algorithm for the Euclidean traveling salesperson problem. Okay. So the steps go like this. First, with respect to the cost function, you compute a minimum spanning tree of G with respect to the cost function C. So you can use Prim's algorithm, Kruskal's algorithm, any other minimum spanning tree algorithm, and this can be done in polynomial time, we know. Then we make a traversal of the tree. First of all, you consider this T as a rooted tree by choosing any arbitrary root. Let us call it U1. Okay, choose an arbitrary vertex U1 of T. Then you make a traversal of U, T starting from U1. Okay, so make a pre-order traversal. I will explain what is meant by pre-order traversal in an example. But anyway, you make a traversal and visit all the cities starting from U1 and eventually come back to U1. Okay. And in the process, you have visited several cities, all the cities actually, and let this be the sequence in which the cities are visited, starting from U1, go to U2, then go to U3, and maybe again come back at U2. So you write U2 here. That's why the number is 2n-1 rather than n-1. Okay. So this is not actually a cycle or a path because there are repetitions of vertices. There may be repetitions of vertices. Or why should I say there may be? There will always be repetition of vertices on this path. So this is essentially called a walk in the tree. Okay. Now when the walk is completed, you look at this list and if you see that some vertex is repeated, so starting from the second occurrence, third occurrence, fourth occurrence, you delete those. Then you will be left with, okay, so you remove duplicates from the list, keep the first one only. Second, third, fourth occurrences will be deleted or removed from this list. But still, since you visit all these these vertices of t starting from u1. This will now give you a sequence of all the vertices of t or of g. Okay. Anyway, G is a connected graph. So just append u1 at the end, because this was also a duplicate, we removed it, but now just append it to complete a Hamiltonian cycle and simply return the Hamiltonian cycle Z. So that is basically the simple-minded, straightforward algorithm. Okay. So in order to see what exactly this algorithm means, I will take an example. Suppose A, B, C, D, E, G, F, these are the locations of the cities, and cost between pairs of cities is the Euclidean distance, like the CD, CE, EG, whatever the costs are. So compute all these pairs of costs, and with respect to these costs, I compute, let's say this is the minimum spanning tree. Okay. Now in this example, I start from any arbitrary vertex, so I start from F. So I list F, that is why I call it a T-order. First list F, then go to any arbitrary neighbor. In this case, I chose to go to E, FE, E2, maybe C. And then from C, you cannot directly jump to D or G or any other vertex without coming back to E. So E to C, you come back to E. E to C, you come back to E. From E, you go to D. Then again come back to E. Go to G. Come back to E. Then come back to F. Then go to A. Go to B. Come back to A. Come back to F. So my work is precisely this: F, E, C, E, D, E, G, E, F, A, B, A, F. So what are the duplicates? This is a duplicate, this is a duplicate, this is a duplicate. This is a duplicate, this is a duplicate, this is a duplicate. So if I remove all the duplicates, I will be left with F, E, C, D, G, A, B, that's all. Okay. And now since I want to come back to F, I just add F at the end. So this gives me this cycle: F, E, C, D, G, A, B, F. Okay. Let me now prove that this TSP cycle produced by the algorithm is not more than twice as bad, twice as the cost of the optimal TSP cycle. Okay. So we will continue to use the previous notations T, W, Z and so on. So what is the approximation ratio? So let us say Z is the Hamiltonian cycle returned by the algorithm, and Z star is an optimal, that is a minimal Hamiltonian cycle. I want to compare the cost of Z and that of Z star. Okay. Now if I first look at Z star, it's a Hamiltonian cycle. If I remove any edge from Z star, I get a Hamiltonian path. Okay. And the Hamiltonian path is also a spanning tree of G. Okay. It is connected and contains exactly n-1 edges. It's also a spanning tree. But T is my minimum spanning tree. So the cost of Z star minus an edge, cost of an edge, cannot be larger than the cost of T. Okay. So I can say that actually this is a two-way thing. If I remove edge E from this, cost of t is less than equal to cost of z star minus E, and this is less than equal to cost of z star. So these two things together I have written like this. Cost of t must be less than equal to cost of z star. Then an important thing about this construction is that, just go to the construction, you see that each edge is used twice. One for going down, second time for going up. This, then this, this. So the initial walk has a total edge cost which is equal to the sum of, okay, let me write down. Yeah. So the initial walk has total cost which is twice the cost of the tree, edges of the tree, because each edge of the tree is traversed twice, once for going down, another time for going up. Okay. So now now consider, of course, I am not outputting this W itself as my TSP. What we instead do, there is another process involved, that is removal of duplicates. Okay. So this step we have to consider. So what happens to cost of W by this duplicate removal process? Okay. So what is a duplicate removal? It's something like this, changing U, V, W to U, W, because because this duplicate removal means that V has appeared somewhere earlier. Of course, it cannot be here, must be somewhere earlier. Therefore, I can find some U here, and okay, W is anyway, let us say it's in the middle. Otherwise, you simply remove V, doesn't matter. So, duplicate removal means you simply remove this V and shorten that tool from U, V, W to U, W. Now, since we are talking about Euclidean distances, the cost of U plus V plus cost of V, W must be greater than equal to cost of U, W by the triangle inequality. Okay. So, cost of U to V, U, V plus cost of V, W is greater than equal to cost of U, W, that is by the triangle inequality. So, by removing this duplicate vertex V, you are not increasing the cost of the walk, right? So, the cost of W does not increase by duplicate removals. This happens because of the triangle inequality. Then, what does it mean? Final Z, final tool that I consider, CZ, its cost is less than equal to the cost of W, which is equal to 2 times the cost of the minimum spanning tree, and this cost is less than this, so 2 times this is less than 2 times cost of Z star. Therefore, the approximation ratio is CZ over CZ star is less than equal to 2. So, this is a 2 approximation algorithm. Okay, so I raise a question which is not answered here. So, you just think about, is rho tight. So you try to answer this question. So anyway, for the Euclidean traveling salesperson problem, I can therefore arrive at an approximation algorithm which gives me TSP tours not worse than 2 times the optimal TSP tour. Okay, good. But now we have been talking about Euclidean traveling salesperson problem where this triangle inequality holds. In fact, whenever this cost function satisfies this triangle inequality, we have a 2 approximation algorithm. It need not be Euclidean TSP, right? But in a general situation where you deal with arbitrary cost function, which is not bound to satisfy this triangle equality, can we arrive at some such algorithms? Next, show that this is our second example, but I will show that no such approximation algorithm can exist unless P is equal to NP. So, this general traveling salesperson problem is not approximable. So, that is what is meant by inapproximability. Okay. In short, I will now prove this statement for any constant rho greater than 1. The existence of a polynomial time rho approximation algorithm for the general case of TSP implies that P is equal to NP. Okay. So, the popular belief is P is not equal to NP, therefore by contraposition there cannot exist any rho approximation algorithm for general traveling salesperson problem. Okay. So, how do I prove this? I prove it by contradiction. I suppose that there exists a hypothetical algorithm A, hypothetical polynomial time algorithm for A, which is a rho approximation algorithm for the traveling salesperson problem, the general traveling salesperson problem. Okay. Using this hypothetical algorithm A, I can solve the Hamiltonian cycle problem in a graph G in polynomial time as follows. So, I essentially make a reduction from the Ham cycle problem in some graph to TSP. Okay. So, how does this reduction work? Let us see. Okay, so let G be an instance of Hamiltonian cycle with V equal to N, size of V with N vertices. Now, this is a general graph. This is not a complete graph. Okay. So, E may contain some of the edges. It may also not contain some of the edges. Okay. So, I will now compute a complete graph on this vertex set. Okay. I will keep the vertex set JP, but I will change this edge set to E prime, which now consists of all possible edges connecting these vertices. And now I will take cost function like this. If E is an edge in E itself, then I will take the cost of that edge to be 1 over N. N is the number of vertices. If E is not an edge here, then I will take its cost as 2 times rho. Okay, this is a simple construction. 1 over N if E is in E, otherwise 2 rho, which is if E is not in this set. Okay. What does it really imply? Suppose that the original graph G, okay, fine. So now simply run this hypothetical algorithm on G prime. So it will give you some suboptimal TSP2. Okay. Now let us see what the cases are. Suppose that this actually contains a Hamiltonian cycle. Then this means using these edges I can complete a TSP2, and definitely that tour is one of the optimal tours having a total cost of 1. Right? So if G contains a Hamiltonian cycle, the optimal TSP2 has cost 1. Okay. But A is a row approximation algorithm. So it will return a tour of cost less than equal to rho. Rho times 1, which is rho. But then this tour cannot contain an edge of cost 2 rho, because 2 rho is bigger than rho. And this algorithm returns a tour of cost less than equal to rho. So it cannot use any edge of this cost. So in particular, this implies that A will return an optimal TSP2, because any Hamiltonian cycle whose cost is less than equal to rho must be a Hamiltonian cycle whose cost is 1. Okay, because if you involve any edge of cost 2 rho, it will become too big. Okay, so in this case, A will actually return an optimal TSP2 whose cost is 1. Okay. On the other hand, if the original graph does not contain a Hamiltonian cycle, then in order to obtain a TSP2, you have to include edges of this cost. Now the optimization problem is actually to reduce the number of edges with this cost, but at least one such edge must be included, because G does not contain a Hamiltonian cycle. Okay. Then any TSP2 must use at least one edge of cost 2 rho greater than 2, and therefore the optimal Hamiltonian cycle will have cost at least 2, and since this A is a row approximation algorithm, it will produce something. It will give a I would say it will return a TSP2 whose cost is at most rho times that. In any case, in this case, A will return a tour whose cost is bigger than 2, and in this case, A returns a TSP2 whose cost is equal to 1. Okay, so here it is 1, here it is greater than 2. Okay, therefore, by looking at the cost of the returned tour, or the tour returned cycle returned by this hypothetical algorithm A, I can decide whether our original graph contains a Hamiltonian cycle or not. But then this, I would say, if this is a polynomial time algorithm, this reduction also takes polynomial time, and then it's just a matter of looking at the cost of the cycle returned by A. That is also polynomial time. Therefore, if such a hypothetical algorithm A exists, I can decide, okay, sorry, here is a mistake. If G prime, no, it's not G prime, if G does not contain, so this is just G. Sorry, if G does not contain a Hamiltonian cycle. Okay. So This gives us a polynomial time decider. Existence of A gives us a polynomial time decider for the Hamiltonian cycle problem. But we know that the Hamiltonian cycle problem is NP complete. Therefore, the existence of a polynomial time decider for this Ham cycle problem will imply P is equal to MP. Okay. So, under the assumption that P is not equal to NP, this general travelling salesperson problem is not approximable. So, maybe I just leave you as an exercise. Of course, here I have assumed that rho is a constant. So, can we have something like rho equal to log n? Can we even have rho equal to n? Does it make enough sense? We'll just think over this. Okay. So, this construction can be used when rho is equal to log n or rho is equal to n even. Okay. So, I leave it to you as an exercise. Okay. Okay. So, this interesting inapproximability result shows that not all difficult problems are approximable. Okay. There are some problems that resist to approximation possibilities. Okay. Okay. So, that's an interesting and important result in the theory of approximation algorithms. Now, I come to a different paradigm of designing approximation algorithms. To start with, this looks like a completely different problem. So, what is a linear programming problem and how do I use it to design approximation algorithms? Okay, so let me introduce this problem first. Suppose that x1, x2 through xn are real valued variables and we also assume that they are greater than or equal to 0. Okay. Now, this is also an optimization problem. So, we want to minimize or maximize a linear function of these variables, that is of this form a1 x1 plus a2 x2 plus an xn, where these coefficients a1, a2, an are constant values, positive, negative or even 0, everything is allowed, subject to a set of linear constraints of the form, okay, something like this u1, u2, un, these are all again constant values, positive or negative. So, this linear quantity is something like this. So, this notation means this can be an equality constant, this can be a less than equality constant, or it can be a greater than equality constant. So, these are all constants, positive, negative or 0. And this is either equality or less than equality or greater than equality. Okay, so less than and greater than are not allowed in the current context. Okay. There is a reason for this, but anyway, let's not worry too much about this. And how do I solve linear programming problems? Okay, so there are several methods. Two popular algorithms are called simplex method and interior point method. Simplex method is perhaps the most widely used LP solver, although its running time is maybe fully exponential in the number of constraints. Okay. But this pathological worst case scenario, these cases are very, very rare. So, people normally use simplex method. This is a polytime algorithm, but people usually use simplex method. So, we will not look at what is the simplex method, and let us just assume that there are good algorithms for solving LP. Okay. So, in fact, if you have to solve some LP instances, there is an interesting package, an API, GNU Linear Programming Kit. So, you can use this. It's a fairly efficient thing, not the most efficient toolkit for this, but you can anyway use this. So, let us assume that this real valued optimization problem can be solved efficiently. And I will just give you a simple example of an LP instance in 2 dimensions. Suppose that this is the objective function x1 minus 2x2, f of this, and I want to minimize or maximize this subject to, let's say, these 6 constraints. These are all linear constraints. This is greater than equal to, this is less than equal to, 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 something like this. Okay. So if I now draw the picture of these constraints, the regions of these constraints are considered, these are all half planes, right? And if I intersect all these half planes, this will look like this shaded region. So this is C1, C2, this C3 this direction, C4 this direction, C5 this direction, C6 this direction. Oh, this may be C. No, this is not C7. This actually says x1 greater than equal to 0. This says x1 greater than equal to 0. Yeah, that's true. And recall that we wanted to, this is our objective that we want to minimize or maximize, x1 minus 2x2. So if I put that is equal to 0, x1 minus 2x2 equal to 0, I get this line. This is x1 minus 2x2 equal to 0, f equal to 0. And if I go in this direction, f becomes less than 0. If I go to this direction, f becomes greater than 0. Okay, the more and more I move away from this f equal to 0 line, the more negative this becomes. And the more and more I move away from this f equal to 0 line in this direction, f increases. Okay. So, you see that, therefore, but all the constraints must be satisfied. Okay. So, you cannot go beyond this shaded region. Okay. So, you see that the minimum is achieved at P3, whereas the maximum is achieved at P6. Okay. Fine. So, that's about LP and one particular example to motivate you what it does. Now, how does this linear programming problem fit in the current context, given that we can already solve them efficiently? So this is how I explained, this is how this can be done. I explain in the next couple of slides. So once again, let us look at the minimum vertex cover problem. Now, there are several steps in the process. One is called formulate, which means I have to somehow formulate the minimum vertex cover problem as a problem in LP. Then there is a step, I will explain that, relax that instance. Then third step is solve the LP. And then there is a fourth step called round the solutions, the LP solution, to a solution of the original problem. These 4 steps together will give me an approximation algorithm for the original problem, minimum vertex cover. So one by one, let us see all these 4 steps. Of course, solve the LP I will not show. We will assume that there are good LP solvers, efficient LP solvers. So I will explain this formulation, relaxation and rounding steps. Okay, so once again, suppose I want to find a minimum vertex cover U in an undirected graph G equal to V comma E. So I will introduce variables XU for each vertex U in V. Okay. Now I will interpret the value of XU in this fashion. If U is included in the cover U, I would like to have XU equal to 1. If U is not included in the cover, then I will have XU equal to 0. So this is the interpretation of this variable XU. 1 if U belongs to U, 0 if small u does not belong to the cover capital U. Okay. But then what do I want to minimize? I just want to minimize the sum of these XUs, that is the size of the cover U. Okay. So I want to minimize the sum of XU values, where U is over, U runs over vertex set V. Okay. So I want the minimum number of U's to contribute 1 to this sum. Right. So in that sense, this is the minimum vertex cover problem. And what are the constraints? The constraint is that every edge in this graph must be covered. Okay. Therefore, for each edge U comma V in E, I must have XU plus XV greater than equal to 1. Okay, which means either U covers U comma V or V covers U comma V, or maybe possibly both. Okay. So this is how I formulate the minimum vertex cover problem as an LP problem. Okay. Now there is a catch. XU, these variables are now no longer real valued. These are, you may call, integer valued or 0, 1 valued, Boolean valued. Okay. So this is the first important and interesting observation. XU are integer or Boolean valued variables. They are not real valued variables. This is where the relaxation step comes into the context. Okay, so relaxation and rounding. Although these XU are Boolean valued or integer valued variable, for the moment I will treat them as real valued variables. Okay. And this is called the relaxation step. You relax the domain of values of XU from 0, 1 to anything real between 0 and 1. Okay. Now, then you get an instance of LP, real valued LP. Solve it. And let us say this bar things, XU bar, U in V, is a solution. Okay. These are now no longer 0, 1 valued. Okay. These are some, okay. We will also impose a restriction that this XU should be greater than equal to 0 and less than equal to 1. Okay. So these are all values between 0, 0 and 1, in the interval 0, 1. Okay. So we have got this solution. Well, this is optimal solution obtained by LP solver. Okay. Based upon that, we will arrive at a solution of the original problem like this. So effectively round these values to the nearest integer. That means if this quantity is greater than equal to 0 but less than 0.5, I will take XU equal to 0. If this is greater than equal to 0.5 and less than equal to 1, I will take this as 1. Okay. So this is rounding in the literal sense. Okay, this is what we mean by rounding. Then I have to show that if I choose XU values this way, I continue to have, now whatever this XU recommend, this will be a vertex cover. Okay. Why? Because I have taken the constant for every set, every edge UV. I have the constant this plus this greater than equal to 1. This says that this and this cannot both be less than 0.5. At least one of them, or maybe both of them, are greater than equal to 0.5. If so, I have taken either XU equal to 1 or XB equal to 1 or both. Therefore, every edge U, V is covered by these assignments. Okay. So, this is a feasible solution. Now, the question is, how bad is this from an optimal solution? Okay. These things we have to derive now. Okay. First, note that if this is less than 0.5, I am taking this equal to 0, and 0 is anyway less than equal to 2 times this quantity. Okay. This is anyway greater than equal to 0, so I always have this. Okay. On the other hand, if this is bigger than 0.5 or bigger than or equal to 0.5, then I am taking XU equal to 1. Okay. If this is greater than equal to 0.5, I am taking XU equal to 1. But if I multiply this by 2, 1 is less than equal to 2 times X, this real valued solutions. Okay. So in either case, I have the rounded value is less than equal to 2 times the value returned by the relaxed LP solver. Okay. And therefore, if I add them up, we have this inequality. Summation of XU, U will be less than equal to 2 times summation of this. Okay. Now suppose that, now let us look at an optimal solution of the minimum vertex cover problem. Okay. Now XU star correspond to a minimum vertex cover, and these values, because this is a cover, they will satisfy these constraints. Okay. Because this is a cover, okay, they satisfy all the constraints. Therefore, these XU star values are also a feasible solution of the LP instance. Okay. But this is not necessarily an optimal solution, but this is a feasible solution. This XU star corresponding to a minimum vertex cover satisfy all constraints, but this is our optimal solution of the LP, and this gives us some solution of the LP. Okay. In any case, I can write this sum, which we wanted to minimize, is less than equal to sum of these quantities, because this is also a feasible solution, but need not be optimal. Okay. Therefore, I now piece together all these inequalities. This is my size of the final vertex cover. This is less than equal to 2 times this, and this sum is less than equal to this, so this is less than equal to 2 times this. Okay. So, to sum up, this is less than equal to 2 times this, and then I use this 2 times this. So, this is the number of vertices in the vertex cover returned by this algorithm. This is less than equal to 2 times the number of vertices in an optimal vertex cover. And therefore, the approximation ratio is this by this sum by this sum, which is less than equal to 2. Okay, so approximation algorithms have a very intimate connection with linear programming and this process that is illustrated here, relaxation and rounding and similar techniques. In fact, the current day studies of approximation algorithms mostly talk about this connections with LP solving and tools concerned with this linear programming. Okay, this is a vast area actually, so I just wanted to give you a flavor of this, how linear programming can be used to arrive at reasonable or good approximation algorithms. This is a far-reaching, this has a far-reaching consequence in the study of approximation algorithm. Okay, so today I stop at this point. As the last topic, in the third and final lecture, I will cover what is called polynomial time approximation schemes. Okay, until then, goodbye.